Hello, everyone. My name is George, and I'm a PhD student in the SciTech group. I'm a fourth-year PhD student, and I'm working on cloud computing and cloud infrastructure for scientific workflows, and also distributed monitoring for scientific applications. So today I'm going to talk about the recent work that we did under the Dynamo project, which is funded by NSF. And the title is Fair Sharing of Network Resources Among Workflow Ensembles. So the outline for this presentation, I'm going to give you a little bit of a background and motivation based on a weather forecasting application. I'm going to briefly touch upon the prior work on Dynamo. I'm going to talk about what was missing and what we did to address that. And also, then I'm going to present like a short evaluation from what we produced. So CASA stands for Collaborative Adaptive Sensing of the Atmosphere. And as you can tell, they're basically doing weather forecasting, and they're trying to figure out severe weather effects in the areas that they have their radars. So CASA differs from the traditional radars in the sense that traditional radars are high power and long range, and they can sense weather changes in the higher atmosphere. But CASA has a short-range Doppler radars, and it can sense weather changes and severe effects like tornadoes or hail in the lower parts of the atmosphere. So CASA has selected to create their radar network in the Dallas-Fort Worth area. And that is because, as you can see on the map on the right, this area presents some severe weather effects. Based on the input and the data collection that you do from the radars, CASA produces a variety of weather products. And on the left side, we can see like reflectivity that shows basically rainfall in the area, and also the wind speed or wind velocity in the area of the DFW. Previously, with Dynamo, we tried to help CASA and make them and enable them to use multiple clouds. And this was done as a part of like a Pegasus workflow. So scientists would create or like would create like Pegasus workflows, and then by using an abstraction layer that we call Mobius, they could interface and interact with multiple scientific clouds, such as the Exogeny Testbed, Chameleon, and other repositories. So that way, CASA enabled them to use data-aware workflow scheduling, and also expand on multiple locations around the US. More specifically, CASA is using, well, I'm going to talk about two workflows, basically, the Wing workflow and the Nowcast workflow. And CASA, in their deployment, they're using Exogeny and Chameleon. And in order to do that, they will create multiple data paths on dedicated links by using the layer 2 networks that Exogeny provides. And also, they're going to use Pegasus to deploy their workflows and HD Condor to create the workflow infrastructure for the execution. But what was missing? So from the prior work, we can see that we needed two different links in order to provide isolation and the compute guarantees and the transfer guarantee and the network guarantees that CASA needed. So we had to solve that. But additionally, CASA has a triggering mechanism based on the new data that arrive they want to create new workflows and submit them. So that also was missing, and we had to address that too. And our approach to address this was to expand our network capabilities with a virtualized exchange, SDX exchange, and also introduce the Pegasus Ensemble Manager into the Casa workflows. So with the virtual software defined exchange, basically we can control exactly how the flows perform on the network. And this is done basically from two components. One is the Exoplex component and the Plexus component. So the Exoplex component creates the entire network layout, and the Plexus component controls how the network performs and what flows can exist on that network. Basically, it uses some security monitors to whitelist or blacklist flows, and also there is a routing and a flow manager that controls the speed of the flow and basically how an individual flow performs on the network. There is also a REST API that we can interact with this Exoplex framework that we talk through Mobius. Secondly, the Pegasus Ensemble Manager is a service that can handle multiple collections, and multiple workflows can become part of a collection that are related with each other. So as you can see on the right side, there can be multiple ensembles that have different configurations. And the Pegasus Ensemble Manager can control how many workflows within an ensemble we plan at the same time, and how many workflows within an ensemble we execute at the same time. Additionally, the triggering functionality, basically the Ensemble Manager has the ability to watch for files or that are located on the local disk or on a web server. As files arrive, the Ensemble Manager will pick them up, bundle them, and create another workflow, and it will be added to a separate ensemble or an ensemble that has been created before. And now for the evaluation. So to evaluate these two approaches, basically we create a network, we create an infrastructure, on Exogeny and Chameleon that is connected via the VSDX slice and the networking that we create. For our evaluation, we have one worker on for the Casa Win workflow on TAC, and 3 workers for the Nowcast workflow, again on TAC. And all the connectivity is done via the layer 2 links with the 1 Gbps bandwidth. So a little bit about the Pegasus workflows now that we used for the evaluation. The first one is the Casa Win workflow, and the structure, you can see it on the left side. So this workflow has a first layer that gets input files and has to unzip them. And then based on the unzipped files, it calculates a max velocity grid. And from that point on, we calculate the images that we show on a web dashboard, or like the GIF I presented in the second slide. And we also can alert points of interest, such as hospitals or other locations. So the Win workflow has 4 compute tasks, and we use Singularity to execute them. And the Singularity image has like 163 megabytes of size. And also the test case we used is about 30 minutes and a total size of 6 gigabytes of data. And we deploy 1 workflow every minute with the Pegasus Ensemble Manager. Similarly, for the Casa Nowcast workflow, On the left side, you can see the structure. It's a little bit different because this one has only 2 levels. And on the first level, basically, it gets a grid input file, split it into 30 different reflectivity files, which correspond to the next 30 minutes. And this workflow has, again, a singularity image that's 153 megabytes. And the test case we used was about 300 megabytes. And again, we deploy one workflow every minute based on the incoming files. So why network sharing was needed for CASA? This slide shows the network needs of wind ensemble. And as you can see, throughout the execution of the ensemble, we don't go over 240 megabps per second on the network. This basically tells us that the wind ensemble doesn't congest the network, and it can coexist with other ensembles. However, the nowcast ensemble, as you can see on the right side, it overly congests the network, and the contention it creates becomes unfair for other ensembles that are like wind, that they allow space for other workflows to coexist with them. So this unfair contention there, we had to resolve it, and that's why we introduced the virtual SDX and also the ensemble manager. So now I'm going to show 2 graphs here, and they're based on the QoS policies that we apply with the SDX. And we have 3 scenarios here. The first scenario is each workflow is on a dedicated link. Its workflow is on a dedicated link. And we can see that the wind ensemble that doesn't congest the network performs really well and really fast, while the nowcast ensemble that congests the network has a great variation in time executions, and also it takes way longer. When we switch to a shared network where the 2 workflows exist at the same time, we can see that the most affected workflow is the wind workflow. And we can see an increase of about 1,000 seconds for some of the executions. While the nowcast ensemble, on the other hand, because it already congests the network, it doesn't perform much worse than its dedicated performance. Finally, we apply the SDX policies on the shared network, and we give 300 megabps bandwidth to the wind workflow and 700 to the nowcast workflow. And we can see on the left side that the wind workflow performs much closer to its original or initial state, while we still increase the runtime for the nowcast workflow, but not by a lot. It's basically, we increased it by 500 seconds when it was 1,800 seconds approximately. So we can see that by applying the SDX QoS policies, we can allow some air for the workflow that doesn't congest the network and provide some more fair conditions for it. Next, we assumed that we can take away the QoS policies of the SDX, and we would like to see how the Pegasus Ensemble Manager on its own can handle that. So we used different execution parallelisms for the nowcast and wind workflow. And on the left side, we have the average workflow makespans for individual workflows within an ensemble. And on the right side, we have ensemble makespans for the entire ensemble. And we can see that for figure 14, for the wind ensemble, as we increase the nowcast execution parallelism, the wind ensemble average makespan increases, and this is the same for the nowcast ensemble. And on the right side, as we increase the execution parallelism, we see that the makespans stabilize around 6 Execution parallelism 6 for the nowcast ensemble, and execution parallelism 8 for the wind ensemble, 6 or 8. And that way we can show that by pacing the workflows and by pacing the ensembles, we can achieve better turnaround times for individual workflows and also reduce the time that the entire ensemble takes to be executed. And this is the last slide.
Any questions for George?
Yeah, I have a question. So George, you're kicking off the workflows every minute, or was it adding it to the ensemble manager every minute and then letting it handle?
Yes. So
running them?
For this case, for the QoS on the Pegasus ensemble manager, we are adding a workflow every minute to the ensemble, but we are allowing the ensemble manager to start the workflow based on the configuration settings we have.
Okay.
While for the SDX, we don't do that. It's unlimited. It's and we dispatch a workflow every time we get one.
Oh, okay. I see. So you did like, I think it's a max running. So you just increase that and then you ran the whole thing again each time. Okay.
Okay.
Any other questions? I have a quick one, George, for you.
Yes.
So when you're doing this, the QoS policies, are you assuming the fine grained it's on the task, or it's the whole workflow? And are you also assuming, for example, that if you get more workflows coming in and out, we're assuming like policies that you can punish, like penalize some workflows and reward some other ones that are just coming in?
Mm-hmm. So we haven't worked on the second part, like penalizing workflows, but penalizing them is also like an outcome of how many of them you can run at the same time. So as more workflows come, but you don't increase your execution parallelism with Pegasus, with the ensemble manager, by that way you penalize the workflow ensemble on its own. For the first question, we are applying the QoS policies on the entire workflow, but the QoS policies are applied on a task level.